Hello everyone. We are going to talk more about the graph algorithms. In this video, we are going to focus on directed graphs, discuss some applications for the breadth first search and depth first search over the directed graphs. Mainly, we are going to focus on connectivity in the directed graphs, different definitions, different problems, and topological sort. We have defined the undirected graphs in the previous video, but in some cases, the problem that you have modeled using a graph is more suitable to be modeled using a directed graph, not an undirected graph. So what is a directed graph? We have a set of vertices, nodes. We have a set of edges between these nodes, but the difference here is that edges are directed. So here, for example, from this node, let's just call it A to B, you have an edge from A to B, but you don't have an edge from B to A. So it means that if you are at A, you have access to B, you can go to B, but if you are in B, you cannot directly go back to A because of this edge, because the edge is directed. So what is the use cases? You can think of any traffic network where the roads are directed, or for example, the World Wide Web, the hyperlinks are directed, right? At some page, you have a link to other page, but it doesn't mean that in the the second page you have a link that goes back to the that refer to the previous page, to the previous web page. To be able to discuss about the problems here, the problems that we are going to solve, I need to define a couple of terms that we refer to them a lot. So edges first. Edges are directed. Sometimes we call them arc as well. So we say that an edge U to V is a directed edge, and we sometimes show it using basically use an arc that U goes to V instead of this pair. And anyway, if you show it using a pair, the first one is called the head and the second one is called the tail. So you have an edge that goes from U to V. So based on this fact that edges are directed, instead of degree for one node, we have two terms for degree. The number of edges that are coming to this node, that this node are the head of the these nodes are the tail. This node is the tail of those edges. So for something like this, if you have a node like this one, the in degree is 3, the number of edges coming to this node, and out degree is going to be the number of edges going out of the node or vertex. So based on that, connectivity in the directed graph is going to completely change. In an undirected graph, if you have a path from a node to another node, you would say that these two nodes are connected, and not only the first one is connected to the second one is also connected to the first one, which means that from the each one you can reach to the other one. But in directed graphs, because the edges have direction from a node, for example, a node S, instead of saying that A is connected to T, you would say that for example, T is reachable from S, or S can reach to T if there is a path like this, that S is the first node in this path, T is the last node in this path, and there are a sequence of nodes. Between all of these nodes, there is a directed edge from S to V1, from V1 to V2, until you reach to T. So T is reachable from S if there you can find such a path, but it doesn't mean that S is also reachable from T. So by changing the definition of connectivity, we will, instead of having this definition that a graph is connected, you would say that a graph is strongly connected if a directed graph, is strongly connected if for every pair of nodes in the graph, both pair are reachable from each other. So for example, here I have two examples of a graph with the same number of nodes and the same number of edges. The first one is strongly connected, but the second one is not. So you can see that in this graph, if you check any two nodes in the graph, both of them are connected, are reachable from each other. For example, from this node, you can reach to this node, to this node, to this node, to this node. And from this node, you can reach back to this node. You can, from this node, you can reach to this node. From this node, you can reach to this node. So all of the pairs of nodes, if you think about them, both sides of the pair are reachable from each other. But this graph is not strongly connected, although it has the same number of edges, because from this node you cannot access to this node or this node. Anyway, if just two of them are not connected, are not reachable from each other, that's enough to say that it is not strongly connected. So although the some directed graphs are not strongly connected, but we can find some components in any directed graph that they are maximally strongly connected set. So for example, in this case, in this graph, I can find two strongly connected components. All of these four nodes are connected to each other, strongly connected to each other. From for each pair that you choose, both sides of the pair are reachable from each other, and this node alone is going to be another component, because this node cannot reach to any other node in the graph. So you have two strongly connected components. So in some cases, we will see that there are some problems that they are looking for a strongly connected component in a graph, and there are many applications for them. For example, in analyzing the social media, based on the people who are following each other, you can think about finding some strongly connected components to, give some suggestions for the advertisement, for the following suggestions, for the friend suggestion in the social media. And there are plenty of different applications in the social media networks for strongly connected components. Another term that we define in directed graphs is directed acyclic graph. We would say that a directed graph is called DAG, or directed acyclic graph, if there is no directed cycle in the graph. So if you think about this example, you will see that although we have a lot of actual cycles if you don't consider the direction over the edges, but there is no directed cycle in this graph. So if your graph doesn't have a cycle, we can order the nodes so that when you order the nodes, all the edges are going to the, for example, if you order the nodes from left to right, all the edges are going from left to right, and there is no edge with the direction coming back from right to left. For example, for this graph that didn't have any directed cycle, I can order the nodes and put them in this order. You can see that all the edges are going forward, all the edges are going from left to right. We call this a topological ordering for the graph. So just compared to graphs, I know that it is not quite intuitive when you look at them, but for example, you see that V1 doesn't have any incoming edge, so I put it at the first, and then V2, and all the edges going out of V1 and V2 goes to the right, and then we just actually order the rest of the nodes so that there is no edge going from right to left. So based on these terms that we defined, we can define many problems. For example, assume we have a directed graph. We wanted to check that if the directed graph is strongly connected. If not, we want to find all the strongly connected components in the graph. We want to check if the our directed graph is acyclic or not. We want to find a topological ordering for our graph if it is acyclic. I'm going to actually just show you basically these two, this set of problems that we have here. They are common problems over the directed graphs. There are many applications for them. I'll add some slides explaining the applications. But basically these 4 question problem can be divided to 2 problems. The problems talking about the strongly connected components and the problems focus on the topological ordering. So I'm going to first solve some simpler problems about the connectivity, reachability, and then we will solve the main problems, finding a topological ordering, finding the strongly connected components. So first, because we are going to solve those problems using BFS and DFS, I'm going to just briefly discuss about the BFS and DFS over directed graphs. So the 2 main algorithms, breadth first search and depth first search, that we discuss over undirected graphs, which almost actually, with a slight change, you can apply them over directed graphs. The only difference here is that when you are checking the neighbors for a node, for the visiting the nodes in both BFS and DFS, you should just consider those nodes that you have an edge to them. So just consider the outgoing edges, not the incoming edges when you are checking the neighbors of a node. Otherwise, there is no difference. Both algorithms that we discussed, they are completely applicable on the directed graphs. So the time complexity of these 2 algorithms over a directed graph are going to be exactly the same as undirected graphs. The time complexity will depend on the number of edges and the number of nodes. This is going to be O of n and m, where here n is the number of nodes and m is the number of edges. Still, the result of the BFS, the BFS tree, is going to show you the shortest path from the starting node to all the nodes which are reachable from that node. So the shortest distance or shortest path property still holds for BFS. The property that we discussed over the start and finish time for the depth first search tree, DFS tree, still holds, which means that if you consider the intervals for the start and finish of all the nodes, they are going to have the parenthesis property. Either the start and finish interval for 2 nodes are going to be completely covered, one of them completely covered by the other one, or they're completely disjoint. So that's why we call it the parenthesis property, something like this, that either they are covering, one of them covered the other one, or they are completely disjoint. So we also have the same property for the DFS tree over the directed graph. The only actually property over these algorithms that we don't have it on the directed graphs is that what we discussed about the back edges to find the cycles and or other properties, but is that we discussed about the edges which are not in the DFS tree, those properties doesn't hold anymore, because some of the edges are going to have, all of the edges are going to have direction. So the edges which are not a part of the tree, they are not going to necessarily be back edge. So we don't have those properties for the edges which are not a part of the DFS tree. Okay, so the first problem that we want to solve here is reachability. I have a vertex S in a directed graph. I wanted to find all the vertices which are accessible from S. You can find a path from S to those vertices. We want to find all those vertices. How can I find and how can I solve this problem? The answer is simple. You can either use DFS or BFS. Be careful, both of them with the same time complexity, with the same efficiency, just different order, will find all the vertices which are reachable from S. So it doesn't matter which one you use, BFS or DFS, both of them have the same time complexity, efficiency, just they visit the nodes in different orders. So we can solve this problem simply using a BFS or DFS. The time complexity is going to be O of n plus m. Another problem over directed graph is that I have a directed graph. I want to check if the graph is strongly connected or not. So in the previous problem, I solved this fact that find all the nodes which are accessible from one given node in the graph. Here, I wanted to check that all the nodes in the graph can reach to all other nodes, or all the nodes are reachable from each other. Okay, the problem seems much more complicated because you are not focusing on one node, you are just checking for all the nodes in the graph. So one thing before actually I give you the algorithm here is that the difference between the directed and undirected graph. If your graph was undirected and you wanted to check the connectivity in an undirected graph, you can simply just do it using one DFS or BFS, right? You could run DFS or BFS over any node, doesn't matter, just randomly choose a node, run BFS and DFS. If at the end all the nodes are visited, you would say that the graph is connected. If some of the nodes are not visited, you would say that the graph is not connected. So just one BFS or DFS would be enough. But here, because your graph has directed edges, we cannot solve the problem this way. So one algorithm, the first thing that comes to mind here is that we can run the BFS or DFS, doesn't matter which one, for all the nodes in the graph, okay, and check that if that node can reach to all other nodes. So it solved the problem for me. You run the DFS over all the nodes, and for each node you check that if you can reach to all other nodes in the graph. The time complexity of this algorithm is going to be n, the number of nodes, multiplied by the cost of one DFS or BFS, which is going to be the summation of the the number of nodes plus the number of edges. So in total, we would say that the term complexity is going to be m plus n. Basically, because you can see that if you multiply these two terms, you would get n power 2 plus n multiplied by m. But the number of edges here usually is going to be bigger than the number of, at least equal to the number of vertices. So we can also actually write it just as the number of edges multiplied by the number of nodes. Or you can actually just keep it as this term, the n multiplied by n plus m. But the thing here is that this algorithm definitely is not very efficient. I wanted to find a faster algorithm to solve the problem, check if the graph is strongly connected or not. So one observation that helps me a lot to solve this problem, to find a more efficient algorithm, is that if you have a directed graph and the graph is strongly connected, if there is, for any node in the graph, let's just call it, for example, for any node that you take from S, there is a path to all other nodes. Okay, so you can find a path to all other nodes. Let's just actually call them the rest. And not only that, there is a path. Let me actually just show you these paths. These are paths, not edges. Okay, so if your graph is strongly connected, it means that if you take any node, there is a path from this node to all other nodes, and there is a path from every other node to this node. So there is a path, you can find a path from all these other nodes to S. And that's enough to check. I can pick up one node, and if I can find a path from this node to every node in the graph, and if I can find a path from all those nodes going back to S, that's enough to prove that the graph is strongly connected. Why this is enough? I mean, I'm just telling you that if you just do this sanity check for any node, for just take one of the nodes and check it for that node, that's going to be enough. This statement here is going to be if and only if. So the proof, I think this is quite intuitive. We can prove it. I have written the proof for you, but the intuition here is that if you take one node and you show that it has a path from, there is a path from S to every node, and there is a path from all those nodes going back to S, that's enough to show that the graph is strongly connected. Why? Because it means that from S to any node, okay, there is a path that is going to this, for example, node V, and there is a path from V going back to S, right? So for every other pair, for example, another node like U, I know that there is a path from S to U and there is a path from U to S. Okay, for the two nodes U and V, you can definitely find a path from U to V and from V to U. How? You can go from U to, for example, you can go from U to S and from S to V, because we know that there is two paths. And you can go from V to S and from S to U. So this check, just if I take one node and show that there is a path from this node to all other nodes, and there is a path from every other node to this node, that's enough to show that the graph is strongly connected. I don't need to run the BFS or DFS over all the nodes. But the problem here is that how can I check, how can I do these two sanity checks? Check that S can reach to every other node in the graph, and how can I check that every other node can reach to S? The first part is easy to do. If I run the BFS or DFS over S and check that all the nodes are visited, I can say that yes, from S there is a path to every other node. So this part can be done in O of n plus m. How about the second part? How can I check that if there is a path from every node in the graph to S? If I'm going to run another BFS, I'm going to run a BFS or DFS over all those paths, all those nodes to find a path to S, that actually makes it exactly the same algorithm that we offered for the that trivial algorithm, right? So that's not going to solve the problem for me. Here I'm going to give you a trick that helps us a lot in directed graphs when we solve a problem over the directed graphs. The thing is, in the second part, we are looking for many paths, but all of those paths have the same endpoint, right? From all the nodes, you want to find a path that end to S. So what if I created a new graph and reversed the direction of all the edges, right? If I do that, the thing is, in this result, this reversal graph, you can run the BFS or DFS starting from S, and because the edges are have been actually reversed, from S in the reversed graph, if you find a path to all other nodes, it's just like you find a path, you can find a path in the original graph from every other node to S. So you can solve the problem using only two BFS or DFS. The total time complexity is going to be O of n plus m. First, create run a BFS or DFS over S. It takes O of n plus m. Then create the reverse graph. There will be some time complexity for creating the reverse graph as well. I'm going to discuss that later. Then run the DFS or BFS over the reversal graph, the reverse graph. And if there is a path from S to every other node in the reverse graph, you can say that the graph is strongly connected. So what is the time complexity of creating the reverse graph? You can see that you just need to reverse the direction of all the edges. So the time complexity, again, for creating the reverse graph is O of n plus m. So here is the full algorithm. You pick one vertex, it doesn't matter which one, just pick one vertex, run the BFS or DFS over starting from S over G, then create the reverse graph, then run the BFS or DFS over the reverse graph, again starting from S. If all the nodes are visited in both BFS and DFS, they would say that the graph is strongly connected. The time complexity of this part is O of n plus m, this part is O of n plus m, and the time complexity of creating the reverse graph is going to be O of n plus m as well, because you just need to check all the nodes, and for all the nodes reverse all the edges. The time complexity is going to be n plus m. And to prove actually the algorithm works, is just basically the whole idea of the algorithm comes from that observation. There is a proof for that. I have actually written the proof, the forward and backward for the if and only if statement. You can read it later just to check that how to write it, but it was intuitive. I just give you the idea that how what is the intuition here. So the next problem that I wanted to solve is I have a directed graph. I want to check if there is a directed cycle in the graph or not. So this graph here, this is a directed graph, although it's not quite clear, but you don't have any directed cycle in the graph, which means that I can actually write the graph by just kind of put the nodes in some specific order. We call it topological ordering. It's just like you are sorting the nodes in a way that there is no edge going from right to left. All the edges are just going forward from left to right. So basically these two graphs that I actually write here, they are isomorphic, they are the same. I just put the nodes in different order, in some specific order that creates this topological ordering for the graph. So to solve this problem, just checking that if the graph does have a cycle or not, I'm going to actually show you two different algorithms. But before that, I wanted to actually give you some theorem or some, in fact, you can also say it an observation, a lemma, or whatever you can prove that. The thing is, if your graph is acyclic, you can actually create a topological ordering for that, and vice versa. If you can write a topological ordering for a graph, it means that the graph is acyclic. So here again we have if and only if a statement. If your graph is acyclic, you can have a topological ordering for that, and if you have a topological ordering for that, you can say that the graph is not acyclic. So this statement here again is if and only if. A directed graph G is acyclic if and only if it has a topological ordering. This observation basically helps me to find an algorithm that to solve actually both of them. The thing is, I can if I wanted to actually check if the graph is acyclic or not, I can just write down an algorithm to find the topological ordering over the graph. If the algorithm can find the topological ordering, not only it finds the topological ordering, but also it tells me that the graph is acyclic. Okay, so that observation, that we can also call it a lemma, a theorem, whatever, you can basically prove it. The backward way of this if and only if is that if there is a topological ordering, definitely there is no cycle, because it is intuitive, because all the edges are going forward. There is no edge going back, so it's not possible to have a cycle. For the forward way, if the graph is acyclic, there is a topological ordering for the graph. I'm going to show it to you by finding an algorithm. Before I give you the algorithm, I'm going to show you a couple of lemmas here as well. So if you have directed graph which is acyclic, there is no directed cycle in the graph, you can definitely find at least one node in the graph which in degree the number of edges coming to the node is 0. At least there is one node in an acyclic directed graph where the in degree for the node is going to be 0. So I can prove this one, but here is the intuition again. Just assume that you have a graph which is acyclic, you have a directed graph which is acyclic, and you don't have such a node. You don't have any node with in degree 0. So all the nodes have some edges coming to them. So in that case, if you think about, for example, the any node V, for all the nodes you are actually claiming that there is an edge coming to this. At least there is at least one edge coming to this node, right? So follow the edges in a backward way. So from the node V, just follow the edge which is coming to V. It goes to another node, for example, U1. Then follow one of the edges, doesn't matter which one of the edges which is coming to this node. This will actually reach to U2. And just continue. Because all the edges are going to have at least one edge coming to them, you can continue. When you are going to stop, whenever you find one of these, the nodes that you have already visited before. And definitely you will find some repetition. Why? Because you cannot go forever. It's not possible to have infinite number of nodes. The number of nodes in the graph is limited, is finite, and because all the edges, all the nodes are going to have some incoming degree, if you continue just following all the backward edges, definitely you will find some repetition. And whenever you find the repetition, you find a cycle. So the graph is not going to be acyclic. This is contradiction, right? The full proof, you can actually just write it. This is the proof. You can just write it verbally. And this is going to be the proof that definitely if your graph is acyclic, there is at least one node with the in degree 0. Okay, if you find such a node, you can find the topological ordering. How? I can just search for the node which has the in degree 0, put it as the first node in the topological ordering, and remove that node from the graph. The graph is going to be G minus V. You remove the node, you remove all the edges for that node. The remaining graph again is going to be acyclic, right? In the previous graph there you don't have a cycle. When you remove V, still the graph is acyclic. So it means that you can still find another node with the in degree 0. So that can be the candidate for the next node in the topological ordering. Just remove the next node with the in degree 0, put it as the second node in the topological ordering, and just repeat until you just ordered all of the nodes in your topological ordering. So this is the first algorithm to find the topological ordering for the graph, for an acyclic graph. But what is the time complexity of this algorithm? Search for the nodes which has in degree 0, remove it. You at least have one node with this property, remove it from the graph, and just repeat this procedure. The time complexity, the way that I wrote the algorithm here, is not quite clear, but you can solve this problem. You can write an algorithm for this. You can implement this algorithm with the time complexity of O of n plus m. And how? I'm going to actually leave it as an exercise for you, but the problem is the algorithm is going to be very simple. Here, the hint for you is that count the in degree for all the nodes once, store them in an array that so that for every node you know that what is the in degree, then and in that round, what is going to be the time complexity of counting the in degree for all the nodes? It is going to be O of n plus m. While you are doing that, find all those nodes which has the in degree 0. Put all of them in a queue using a queue and just one array, and this pre-processing that calculate the in degree of all the nodes. You can implement this algorithm in O of n plus m. You can just put all of those nodes with in degree 0 into the queue, and just remove one node from the queue, put it as the ordering in the topological ordering, and for removing it from the graph, to simulate this part, you just need to decrease the in degree of all those nodes which there is an edge from that node v to these nodes u. You are going to just change the in degree for all these nodes, for example u and w, right? You can do it by just following the edges, just equal to the number of edges, and change the in degree, decrease the in degree for all of those nodes that there is an edge from v to them. So basically I gave you the algorithm. That's it. You can just analyze that the time complexity of this algorithm is going to be O of n plus m. But here I'm going to show you another algorithm to find the topological ordering for an acyclic graph. And not only because the algorithm is nice, the previous algorithm was efficient enough, but this algorithm, I care about it because we are going to use it. I mean, the whole idea here helps us to solve the next problem, which is about the strongly connected component. So in the second algorithm, we will use a depth first search. In the previous algorithms, you can, here in this algorithm, we don't use DFS or BFS. You can see that we just count the in degree, and based on the in degree, we find the topological ordering just by ordering the nodes and updating the graph, removing each node from the graph. But in the second algorithm, I'm going to use DFS. What I'm going to do here is that I can run the DFS over the graph and find the DFS tree and the start finish time pairs for all of the nodes. There is a specific property for the start finish time of the nodes if you run it over a directed acyclic graph. One thing before actually I go to the details here is that if you run the DFS over a directed acyclic graph, the result, depending on which node you start your DFS, the result of the DFS tree is going to be completely different. You may get not a single tree, but a set of trees, right? Because this is an acyclic graph. Definitely this is not strongly connected, right? So it depends on which node you start to run the DFS, the result can be a set of trees, not just one tree. In that case, we call it a DFS forest. If the result of running the DFS is going to be a forest, a couple of trees, we call it a DFS forest. So for example, in this graph, if I started from node 1, if you run the DFS, you get a single tree. From 1, you go to, for example, 3. From 3, you go to 5. From 5, you can go to 2. From 2, you can go to 6. And then you can see that from 5, you actually just go backward from 6 to 2, from 2 to 5. And again, from 5, you can actually visit 4 as well. So it's going to give you a single tree like this. Or if I start, for example, from a different node, like 6, for example, you can see that 6 only have access, there is just one edge going from 6 to itself. So 6 only can visit itself, that's it. So this is going to be one tree, just with one node. And then if you run the DFS again over one of the nodes which is not visited, like 5, then from 5 you can visit 2, 4, and 3. So this is going to give you another 3. And if you, again, because there are still some nodes which haven't been visited, you can just randomly choose another node which hasn't been visited. Here we only there's only one more node which hasn't been visited, 1, and so 1 can only visit itself. So you have 3 trees, DFS trees, and the result is going to be a forest. But it doesn't matter if you run it, doesn't matter which node you start, either if you get a forest or a single tree, there is a very nice property over the start and finish time for the DFS, for the start and finish time, the resulting of those interval start finish times for all the nodes. So think about it. Run the DFS using, for example, in this direction, or for example, something like this. Run the DFS and think about the start finish time that you get for all of these nodes and see that what is the property. I am going to just simulate it here for both of these two trees so that you can actually see what is that observation, what is that great property that we have. So for example, I'm going to first do it using the tree like this. You start from node 1. I'm going to write those start finish time here, because if I write it over the graph, this is going to be too much, because I'm going to run it 2 different times. So you start from node 1, the starting time is 1. Then you go to the node 3, the starting time is going to be 2. For 5, the starting time is going to be 3. From 5, assume that you go to 2. It doesn't matter 2 or 4. Here we are going to 2 because from 4, I mean the 3 is in this way. So for 2, the starting time is going to be 4. For from 2 you go to 6. For 6, the starting time is going to be 5. For 6, there is no other node that you can go from 6, so the finish time for 6 is going to be 6. You go back to 2. There is no other node that you can visit from 2, so the finish time for 2 is going to be 7. The finish time for you go back to 5. From 5 you can visit another node 4. The starting time for 4 is going to be 8. From 4 you can't visit any other node that hasn't been visited, so you finish. The finish time for 4 is going to be 9. From 4 you go back to 5. There is no other node to be visited, so the finish time for 5 is going to be 10. The finish time for, you go back to 3, the finish time for 3 is going to be 11. You go back to 1, the finish time for 1 is going to be 12. Okay, so these are the start finish time for this DFS tree. Let's just run it over this DFS forest as well. We start the DFS over 6, so the starting time is going to be 1. And from there is no other node that you can visit from 6, so the finish time is going to be 2. Then you reset again, choose another node. Let's just assume this is 5 that hasn't been visited. The start time here is going to be 3, right? The time is global, so the start time here is going to be 3. From 5 you go visit 2. So the start time for 2 is going to be 4. From 2, there is no other node that hasn't been visited, and you can go to that. From 2, there is only actually an edge to 6, but 6 have been visited before, so I can't visit 6. So the finish time for 2 is going to be 5. You go back to 5. At 5, you can visit 4. the start time for 4 is going to be 6. From 4 you can visit 3. The start time for 3 is going to be 7. At 3 there is no other node that you haven't visited before, so you finish. The finish time is going to be 8. From 3 you go back to 4. The finish time will be 9. From 4 you go back to 5. There is no other node that you can visit from 5, so the finish time is going to be 10. Now you reset and run the DFS over another node that hasn't been visited. So there is only one that hasn't been visited. The start time is going to be 11. And there is no other unvisited node to visit from this one, so the finish time is going to be 12. So now you can see that the intervals, the start-finish intervals for the result of DFS in two different trees or forest that we can get is completely different from each other. But still there is a very nice property which is common over any DFS. If you run the DFS, it doesn't matter which order of the nodes you choose, but there is a single property about the time of the nodes that you are visiting them. I'm going to actually give you that observation if you haven't found it. But the thing is that you can see that what is the node that has the latest finish time? Which node has the latest finish time? You can see that in both of these two cases, the node 1 has the node 1, I couldn't actually find the word. The node 1 has the latest finish time. Okay? It doesn't matter if you run it starting from 1 or the 1 is going to be the last node that you visit. The latest finish time is going to be the node that has, the in degree 0. You might actually just say that I might have more than one node with in degree 0. It doesn't matter which one, but one of those nodes that has in degree 0 is going to have the latest finish time. So it doesn't matter which one, the node that has the latest finish time is going to be the one with in degree 0. And basically that property that I'm going to give you is that if you order the nodes based on the latest time, you order the nodes in reverse order based on the finish time, you can give a topological ordering for your graph. So this is that claim, that observation that I was going to actually discuss. The simpler form of that observation. We would say that if the graph is acyclic, for every edge uv, the finish time of v, you can see that here I have it means that there is an edge from u to v. If there is an edge from u to v, definitely the finish time of v will be smaller than the finish time of u. I think here this is quite intuitive why this is the case, because either you are going to visit v through u, it means that you will visit actually u first and then you reach to v through some of actually those paths or either the edge here, or you will visit v from through some other node, and because there is no edge from v to u, it is quite clear that there is no edge from v to u, or there is no path from v to u, because the graph is acyclic. Okay, so either V will be visited through some other node completely before U, or V will be visited because of U. So I have two different cases. So the first case is that a start time of V is before the start time of U. If the start time of V is before the start time of U, we know that definitely the finish time of V will be smaller than the finish time of U. It's just like you have completely disjoint intervals. The start time and finish time of V is going to be completely a disjoint interval than the start time and finish time of U. It basically means that V have been visited through some other node. Something like this, that for example for 6, the start finish time, remember, was 1 and 2, right? Because there are some edges from, for example, 2 to 6, or for example 4 to 6, the start finish time of both 2 and 4 will be greater than the 6. So definitely the finish time for those nodes are going to be greater as well. Or the other actually case is that if the start time of U is smaller than the start time of V, it means that you are going to visit V either through U or through some path starting from U. Okay, so the start finish interval of V is going to be completely covered by U. Something like this, that the start finish time of 6 was completely covered by 2, 4, 5, 3, 1, all of these actually nodes. So this gives me actually the algorithm. The total algorithm is that run the DFS and then just put the vertices based on the finish time, the reversed finish time, or the visited based on the reversed finish time. After that, because we don't know if the graph is acyclic or not, but if you put the items in this order, this is going to be a valid topological ordering if the graph is acyclic. So the last part of this algorithm is that after you put the items in that order, you should check if the graph is really acyclic. You can go over the order of the nodes. So for example, this in the second step, you get some ordering of the nodes. You can simply just go over all the nodes and check the check the edges. If all the edges are going forward, you can say that yes, the topological ordering, the order that you get is really a topological ordering. But if you find some node that has some edge going back, going from right to left, you would say that no, the graph is not acyclic, there is going to be a cycle in the graph, and so definitely you don't have a topological ordering for the graph as well. So what is the time complexity of this algorithm? The time complexity of running DFS is going to be O of n plus m, right? The checking the topological ordering at the end is going to be O of n plus m again. You just need to check all the nodes in the order that you find here and check the edges for all of them, right? That's it. That's the only actually thing that you need to do here. So the time complexity of this step and this step both is going to be n plus m. How about the middle one? What is the time complexity here? If I'm going to sort the nodes based on the finish time, be careful. Don't use the sorting algorithm. If you sort the algorithm here, if you sort the nodes here, you are going to add some n log n time complexity, which you have to actually keep it at the end. The total time complexity is going to be n log n plus m. Okay, so the time complexity would be something like this. But I don't want to get something like this. I can actually do it without sorting the the nodes based on finish time. What can I do here is that I can modify the DFS, and whenever I finish with a node, I can store it in a separate array. This gives me the ordering of the nodes in a, sorted based on the finish time in a increasing order. You just need to reverse it and it gives you the ordering of the nodes based on the finish time in decreasing order. So the total time complexity is going to be O of n plus m.